So before we move on to the next page, I just want to take one last quick look at the formula for dot product. So remember, if you have two non-zero vectors, x and y, that are in R2 or R3, so that's a restriction that you have to place on the vectors x and y in order for this formula to make sense. But if in that case, we define the dot product of x and y to be, this is the notation here, but the definition was this product of these three factors, the length of x, the length of y, and then the cosine of theta, and theta was the angle between the two vectors, right? So that's the definition of the dot product. So, but there's a couple of problems now that which fortunately we're gonna have solutions for. Well, let's outline what they are first. So the first problem is that this definition is a bit limiting, right? It's only defined for non-zero vectors in R2 and R3. So currently there's no way to discuss the dot product of vectors that are, say, in R4 or R5 or anything higher than 3, really. So that's the first thing. It's a bit limiting. And the other problem is it depends on theta, which makes it difficult to compute. Like if you go back to the definition one last time here, it's simple enough to write this definition down, but if you try to actually compute this for a particular pair of vectors x and y, you have to be able to get your hands on that value theta, or at least you have to be able to get your hands on the value of cosine evaluated at that angle theta, which in practice is going to be challenging to do exactly without having to round it off. So that's the second problem. And we're going to solve them both at the same time. And what we're going to use is something called the cosine law. And this should be something that you've all seen before. If you don't remember it, don't worry about it. If you don't use it very often, then of course you're not going to remember it. So it's not important to memorize this anyway. I'm going to remind you what the rule is. And to be honest, we're not going to use it for anything in this course except this exact issue that we're talking about right now. So, but it's important enough that I'm going to actually remind you what the cosine law is. You can think of it as a generalized Pythagorean theorem. It's kind of like the Pythagorean theorem, except it applies to triangles that are not necessarily right triangles. Right? So this, as you can see, I've drawn a triangle here. It's definitely not a right triangle by any stretch of the imagination. I've tried to draw it as general as possible, not satisfying any specific requirements. But now let's start labeling some things. We're going to label each of the sides with the lowercase letters a, b, and c. So I'm going to put a there, little b there, and little c there. And then we're going to label the angles with the corresponding capital letters, but we'll do it in such a way so that the angle and the side that both use the same letter will be opposite of each other. So for example, this angle is opposite to this side, so I'm going to call this angle capital C. So notice capital C is the angle, little c is the side length, just to keep things straight. So then here we got little a. The angle opposite to this side is going to be this one up here, so here's where we're going to label this angle as capital A, and then this angle will be capital B. Okay, and what the cosine law tells you is the following. Here's the cosine law. It says that c squared is equal to a squared plus b squared. I just want to pause here. I'm not quite done. So currently this is not the whole story. And really, when would this be the whole story? That's if c were a right angle. If c were a right angle, this would be a right triangle. This would be the hypotenuse, and then you'd have the Pythagorean theorem. But this is what you would do when, in general, when this angle is not necessarily going to be 90 degrees, or it's not going to be necessarily a right angle. Well, then you just subtract the following. You just subtract 2 times a times b times the cosine of capital C. So just to be absolutely clear, this is a capital C, which refers to this angle. This is lowercase c, which refers to this side length. So these two c's are different. Okay, so that's the cosine law. And what we're going to do is we're actually going to draw that vector picture again, where we have two vectors x and y in R2 that both start at the origin and go off to their respective terminal points. And then we're going to use that to draw a triangle, and then we're going to see what the cosine law tells us about that triangle. And really, what comes out of it is going to be this theorem. So here's the theorem. Let's say you've got two vectors x and y in R2, and let's assume that they're non-zero, just so that we can, really the non-zero assumption is just so that we can refer to their dot product, right? And the dot product requires that the two vectors be non-zero. So that's the only reason we're making that requirement. But here's what the theorem tells you. It tells you can compute the dot product of x and y just in terms of the coordinates. So you can write the dot product of x and y. You don't have to worry about the angle between them or taking its cosine. You can just take the product of the first two coordinates. So just take x1 and y1 and multiply them. Then do the same thing for the second coordinate. Just multiply them, x2 and y2, and then you're going to form two different products and you're going to add them together. So this is actually just basically, it turns out this is a shortcut. And that's what the theorem says. In order to prove this theorem, we're going to use the cosine law. So we're going to start by doing what I said. We're going to draw that vector picture. So we've got two vectors that both are going to start at the origin, and they're going to have their own terminal points. Right, so we've got a vector here, which normally I do this one to be x, but it just turns out to be more convenient to label this one as the vector y, and then label the other vector as the vector x. It makes no difference in the end result. You don't have to do it that way. You can reverse the labeling if you want to stick with the previous pictures, and you can follow along, and everything will work out just fine as well. Just use the same logic as I'm using. But if you copy the swap that I'm doing, it just makes the algebraic steps work out slightly cleaner. So that's why I'm doing that. And then what's this distance here? That's the distance between the vectors x and y, right? This is equal to d of xy, which, remember, by definition, this is the norm of their difference. In other words, the difference of x and y, right? Subtract y from x and take the norm of the result, and that's what you get.